Hello dear phasmatic friends. Today, logarithms. What's that? Follow me please. First of all, we are going to say that a logarithm is the opposite operation of exponents. For instance, 3 to the power of 2 is 9. The question is, if I have the number 3, what exponent must I put in order to get a 9? Well, the exponent of 3 must be 2 to get a 9. Then, here we have a base, and here we have a base. Here we have an exponent, and here we have the answer of the logarithm. And here we have the answer of this exponent, and here we have the argument of this logarithm. So, if you want to pass from exponents to logarithms or vice versa, you need to take the base. The expression that is on the right side will pass to the left side as an argument, and the expression that is on the left side as an exponent will pass to the right side as the answer. So it is easy to pass from exponents to logarithms, from logarithms to exponents. Another important thing, if someone says logarithm of 100 and you don't see the base will be always 10. So 10 must be raised to what exponent to get 100? To 2. Another thing, we have natural logarithms or Neperian logarithms. That is ln of, for instance, x. If you have ln, the base will always be 2.71828, etc., etc., etc. In another video, we are going to explain why do we have this number. But it is like pi. You must memorize it in order to work with natural logarithms. Finally, I want to say that in a normal scale, we have numbers, and to get the next number, you add normally 1. You add the 1, you add the 1, etc. But in a logarithmic scale, you multiply by something. For instance, by 10, by 10. You cannot start with the 0 because it would be impossible to follow the sequence. But if you start always by 1, you multiply by a number and by a number and by a number, and you get that scale. And why do we need one scale like that? Imagine you have many numbers, and you want to represent them in a very short space in a paper. So if you use our normal scale, you will never finish, because you have the number 3, the number 1000, the number 1,000,000. But if you use a logarithmic scale, in a very short space, you can put many numbers. Scientists discovered that, and they started using logarithms to represent, for example, Richter, for example, Richter with the scale of earthquakes has used a logarithmic scale. So, an earthquake with a value of 7 compared with an earthquake with a value of 8, the 8 is 10 times the earthquake with a value of 7 in the Richter scale. That is, the last number multiplied by 10 gives you the next number, and multiplied by 10 gives you the next number. Imagine an earthquake of 5 and an earthquake of 7. The earthquake of 7 is 100 times the earthquake of 5. This is powerful. In a very short space, you can represent all earthquakes in Earth. That's why if you have an earthquake of 9, everything is destroyed, because it is very, very strong earthquake. Another thing, in ancient times, there were no computers, no calculators, and it was very practical to convert our numbers to another scale in order to make operations very quick. For instance, if I want to multiply 10 times 100, we will get 1000. Very simple example. But what if I take 10 to the power of 1, 10 to the power of 2, 1 plus 2 will give us 3. It is very easy to add 1 plus 2 and get 3, and after that to pass to 1000, because here you have 3 zeros, then to multiply very big numbers. That's why logarithms were a very good invention in ancient times. And now, today, we use them a lot for calculating many things. But that is a subject of another video. Thank you very much, dear Plasmatic friends. See you next time.